Hello, class. Welcome back. This is MO 869, Introduction to Autonomous Vehicles. Lecture 11, Pose Estimation Algorithm. So previously, we covered up to localization information, and then just 1 second. So previously we covered up to here. And then we left off here to review probability and Bayes filter. So now let's come back and cover the rest of the section, which is a pose fusion algorithm. And I'm going to introduce you to 3 methods: Kalman filter, particle filter, and graph-based optimization. So today, like I just mentioned, I will cover pose estimation algorithm and then how that is applied to autonomous vehicles. So last time we derived the Bayes filter, and now we're going to extend that towards Kalman filter and particle filter. So basically, Kalman filter can be derived from Bayes filter, but under a few assumptions. So the Kalman filter assumes the system is linear, and the cost function or the covariance can be modeled by Gaussian distribution. So those are key assumptions, and if we can problem the estimation, state estimation problem, then we can apply Kalman filter, and the method actually becomes quite simple, and the numerical computation becomes very efficient. So this is the Bayes filter we derived last time. So if you come back and look at this, then what it does is it has this update measurement part, which is this part. This part updates, so corrects the distribution based on the measurements, and then there's this prediction state using motion model and the action input to the model. So this is the prediction part, and last time we introduced to this happens. These 2 parts are working together sequentially but iteratively, recursively, and that exactly exactly happens for the Kalman filter. So this is done iteratively, and that means is that we use this system dynamic model, and then we compute this P matrix, and then we use that information in the update measurement part to update the distribution of the system. And here is the measurement model, sensor model. And here is the equation for x, which is a state, and y, where y is z minus hx prime, which is the correction term. So this measurement update part corrects the distribution using the measurement information. So this is how you can see these two analogy between base filter and Kalman filter. So let's take a look at the slide, which visualizes how Kalman filter is operated for a localization problem. So we know current state, and we have measurements, and we predict next step, which is somewhere here. And then using the measurement, we are going to correct the distribution. So the estimated state distribution is going to be something like this. Okay. So this is illustration of that principle, Kalman filter principle. And same goes with map matching, localization using Kalman filter. So we have lane measurements, and then take it back. So this the green distribution was the prior time distribution, and this now vehicle is in the next time step, and using the action and motion model, we can sort of predict the distribution. And then using the measurement, lateral measurements, we can correct the lateral position or distribution of the state estimation. So now we have this somewhat elliptical shaped distribution, because we were able to remove or reduce the distribution in the lateral direction by using these lane information. Okay. And we repeat this process. And when you have traffic signs, you can use that to correct the longitudinal direction. That way, we can keep the distribution small and bounded using these landmarks. So here, lane and traffic sign is they are used as sort of landmarks, and we can use that to keep the distribution small and bounded. Okay. so it doesn't diverge. So this continues, okay? Particle filter, let's move on to particle filter. Particle filter is more general than common filter. Common filter assumed a linear system. So as you can see, these are x dot equals ax plus bu type of linear system model. So these these were vectors and matrices. But for a particle filter, that assumption and then the Gaussian distribution assumption, is not necessary. You don't have to meet those assumptions. So it seems more general, applicable more generally, but then there is a disadvantage. The disadvantage is that you have to go through this sampling process, which can be computationally heavy and slow when it comes to computing these distributions and likelihoods. So let's take a look at Monte Carlo sampling. So let's say we have this rectangular shaped box, and then the area is height times width. And the key idea of this Monte Carlo sampling is that the area object, so for instance, this area, so you want to compute the likelihood of this area over by the entire space, which is the entire space, and we can approximate that by number of points inside object divided by number of points inside rectangular rectangle. So that's pretty simple idea. And in this case, so if you start with Gaussian distribution, we know that the density function, probability density function, looks something like this for normal distribution with mean and covariance. And when we have more general distribution, the idea is that based on this idea, the PDF will be proportional to the density of particles when we sample. If we sample things using Monte Carlo sampling. So here, this example was almost evenly distributed, but in the case of this density function, if we sample things from this distribution model, then we will see more points towards higher density areas, okay? So that's the idea. And the one of the nice feature by using this Monte Carlo sampling is that it can handle any types of PDF, this probability density function. It doesn't have to be Gaussian normal distribution. So that gives you a big benefit. And this is quite often used in robotics and localization problems. And this is an illustration of using a particle filter for a robotic system, indoor robot localization problem. So let's take a look at how this can be applied to vehicle application, vehicle localization problem. So we need to initialize. We can start with uniform distribution, and then we use motion model and action input. Then that will take us to distribution that is, probably highly likely, more spread, because the motion model also introduces uncertainties. Has distribution over time. So that's going to lead to wider distribution over the space. But then we have measurements, and by using the measurements, we can correct, we can update, meaning that we can put more weights on particles that are close to the measurements. So in this example, we are going to put 0 for ones that are far apart from the measurements, and 0.2, 0.6 for these 3 particles. And then that means we are going to resample based on the weights. And that's going to lead to more particles in this area and less so here. Okay. And next time step, we are going to repeat this process, but this is going to lead to, again, distributed points across the space based on the motion model. So that's going to create another distribution that's sort of wider spread out. And we need to repeat this process basically. So we apply, so we have measurements again now, k+1. We can apply the measurements, update the measurement. So we can, remove, things that are, far apart from the measurements, and put more weights on the particles that are closer to the measurements. Okay. So that way we can keep this distribution bounded and small over time. Okay. But like I said, as you can see, this still follows the Bayes filter principle, okay? And Kalman filter was doing the same thing, but it's just that if we assume linear system Gaussian distribution, then we can analytically solve the problem, and the computation becomes very simple. The math becomes beautiful, and we can solve it analytically, and the numerical computation becomes very very simple. But if we relax that assumption, then we need to go through this more general form of Bayes filter, which is particle filter, which does not assume Gaussian. So it may have all kinds of distribution. And we are going to sort of use that distribution by sampling. So we don't know the distribution, but we can sort of mimic or find out the distribution by sampling, and this process introduces more computations. Okay. Right. So what about landmark matching? So if we have a map, then we can do matching. We can apply the matching to keep the distribution, small and bounded. So the principle is the same, but the method is different here. So we need perception results, we need map, and then by matching, we can find out the associated position. But of course, this will also have some error, so uncertainty there. So it's described as distribution. And then we also have GNSS or GPS, but GPS also has error. So using these two information, we can keep the distribution bounded and small, rather than just using odometry or dead reckoning type of approaches. So to visualize this better, so we have perception results. We have perception algorithm that perceives this lane information, road boundary information, and then maybe we have detected a traffic sign there. So and then we have this HD map, and we can do map matching. And we can do that by, so in the case of particle filter, we have these particles over these spaces, and we can do matching for that particle. And we need to apply this perception results aligned with this particle and see that matches well. And if it doesn't match well, then we lower or even eliminate the weight on that. And we repeat this process for all the particles. And for a particle that gives you good match, will give you a higher weight on that particle. So, and then we have GNSS position error. We can model that as a uniform density function. And so that way we don't have to we don't have to care about particles that are outside the distribution range. And we're going to take weighted sum of these information to compute the distribution of these particles. So probably here the position is going to be somewhere like here, right? With some distribution. Okay. And then we are going to we need to repeat this process iteratively, recursively. Predict, correct, okay. All right, let's move on to graph-based optimization. Like I said, today I'm going to just give you a quick idea of how graph-based optimization is done for localization purposes. But in the following lectures, I will talk more about the graph optimization theory in more detail for SLAM problem and application. Okay. So graph-based localization via optimization goes as follows. So we need to construct a cost function where the first term is the motion constraint or motion cost term, and then the second being GNSS term, and the third term is the map matching term. So so you can think of this as sort of dead reckoning, and then these two plays as landmark correction or landmark alignment. Okay, but we are solving that together here. And the objective of graph-based optimization problem is to minimize this cost function. And we have least square method, which allows us to handle this type of least square method formulation. We can minimize the error that gives you the position that minimizes this error. Okay. The motion term is generated by dead reckoning based on motion data. We have motion model. We have it can be kinematic or kinematic and dynamic model. motion model, and then we have a distribution. So that will introduce you distribution over the space after some time step, and we can create this term for motion cost. And we can do the same for GNSS. GNSS also gives you a distribution, and we need to compute this quadratic form for GNSS. And then next we have map matching cost. This is the quadratic form of the map matching cost. Okay, so that also gives you the distribution over space. So we have three distributions. Motion, GNSS, and map matching. But like I said, motion model, if you only rely on motion model, then you can diverge because you can never correct. Okay, but GNSS and map matching will keep it bounded, meaning not diverge, because map and GNSS gives you absolute position, whereas to the dead reckoning and internal sensors only gives you the incremental. The motion model as well gives you the incremental delta information, so it can drift away from the true value. Okay, so this is a quick summary of three post-fusion algorithms. Some are computationally more efficient, some are faster, some are slower, some is more generally applicable when it comes to distribution. Some gives you better accuracy, some don't. So please take a look, and depending on your application and system, and depending on how you formulate this localization problem and what sensors available to you, you need to use the right filter. So nowadays, in the literature, people use all three methods, but in the academia, people use graph optimization a lot because it gives you good performance. And academically, there's more to improve, and theoretically, there are things we can further improve. And then Kalman filter and particle filter is somewhat old methods, but that doesn't mean graph based optimization is always the best choice. If your system can be modeled by linear system and Gaussian distribution, then Kalman filter is definitely the way to go. Okay, so keep that in mind. All right, let's see some applications, how these pose estimation algorithms are applied for autonomous vehicle. This one is a video clip from Baleo, French LiDAR company. And this is the environment. This is a map. And this is the highway scenario. Because this is LiDAR, this clip is created by LiDAR manufacturer. They are definitely using LiDAR as perception sensors, and they are also using GNSS and the map. Okay. So you get the idea. And you do see these landmarks, traffic signs. And then you can see there is a real-time road boundary perception and matching with map. Okay. And this is the result of that demonstration, showing two values, longitudinal and lateral errors. And you can see lateral error is about 10 centimeter RMS, root mean square. And longitudinal error is somewhat higher at about 20 centimeter. Okay. And that's because the vehicle is driving longitudinal direction. So it's moving fast in the longitudinal direction. So there's a higher chance to exposed to higher error. Plus, there is less information in the longitudinal direction. Meaning that, so if you think about it, in the longitudinal direction, things are repeating, meaning that, we have lane information, which gives you lateral information. But in terms of longitudinal direction, there's, things in highway scenario, things are repeating. Unless you have these landmarks, okay? So traffic signs, traffic lights, you can use those information to correct longitudinal position or distribution. But you don't have that information all the time or frequently. So you can correct that whenever those show up, okay? If you go to urban scene, you may have more landmarks, but environment is more complex. So you can get and GPS information is less accurate. So you need to rely more on the map matching and the dead reckoning motion model, okay? And this one is using the signal level HD map for localization. And because it's signal level map, there's a sufficient amount of features or points throughout the space, so we can use that for mapping purposes, localization purposes. And you can see that, can you guys see this part? That's, I believe that's a distribution, the position distribution of the vehicle. And then you can also see here that there is an error between this red line and blue line, right? Can you guys see? So the I believe the red line is the correct value, and the blue line is if you do not use map matching and just rely on dead reckoning. Okay. This is just another illustration video Valeo shared with people for you to look at. Okay. So how is this implemented? Well, we need to get point cloud, and we need to use computer to process that with match with the map. And in this particular system, NVIDIA TX2 was used. And this is the results they shared. Longitudinal lateral error. Note that they use particle filter. And point cloud map was generated using graph slam, which we'll talk more about later. So I am showing some challenges here. Is it sufficient? The semantic and signal level HMAP based localization for autonomous driving. Well, what if the environment changes? Such as construction. Over time, our environment changes. So one of the major challenge in mapping and localization is our environment changes. So how can we maintain and update the map continuously, okay, or semi-real time manner? One idea is crowdsourced based update in the long future. And we can discuss more about this during the discussion session next week. Okay. All right, let me finish here. Thank you for your attention. I will try to record more video if I can this week. And if possible, then I will probably be able to upload a little more lecture recording, probably Monday afternoon. Okay. All right. Thank you.